Hello everyone, it's my honor to present our paper GD-MAE, Generative Decoder for MAE Pre-Training on LiDAR Point Clouds. This work focuses on pre-training on LiDAR point clouds, which aims to recover masked geometric knowledge of inputs by learning holistic representations. However, previous MAE-based methods for hierarchical learning meet the following problems. Firstly, they need a complex multi-scale masking strategy that backtracks unmasked positions to ensure coherent visible regions. Secondly, the minimum size of masking granularity is highly correlated to output tokens of the last stage, which is unfriendly to small objects. Thus, we propose a simpler approach using a generative decoder. It automatically expands visible regions to masked areas, eliminating the need for complex designs. It also unifies multi-scale features into a single scale, enabling flexible masking strategies without intricate operations like backtracking for masking consistency. The core idea is to use an encoder to create multi-scale representations from partial observations of the input. The decoder is thereafter applied to unify the multi-scale features to a determined scale and expand the visible features to the underlying masked area. Finally, the features of masked parts are processed by a head to reconstruct corresponding input point clouds. After pre-training, the parameters of the encoder are used to warm up the backbone of the detection task. To enlarge the receptive field of the visible tokens when deploying extensive masking, we propose the sparse pyramid transformer. Similar to point pillars, the input points are converted to a grid of 2D pillars on the bird's eye view by the pillar feature encoding module. The tokens are fed into 3 stages to generate feature maps of different scales. In the first stage, non-empty tokens are taken as input and processed directly by a transformer encoder with a constant resolution, while in the other stages, tokens are first downsampled by a sparse convolution with a stride of 2 and then passed through a transformer encoder. In stage I, it has Li encoder layers, each of which is composed of 2 sparse regional attention, SRA, and 1 region shift, RS. SRA is applied to perform self-attention on the tokens that fall in the same region, accompanied by the positional embedding based on the positions of tokens in each region. RS is employed by adding offsets of half of the region size to expand the receptive field of the tokens to capture useful contexts. To enable varying masking granularity and unleash multi-scale representations for downstream tasks, we propose the generative decoder to fuse hierarchical features for reconstruction. We first transform the sparse tokens into a dense 2D feature map by scattering back tokens features according to their corresponding coordinates and then performing a series of standard convolutions. The kernel size is set to 3 to automatically expand visible features to potentially masked areas. Finally, we obtain masked features by indexing the feature vector on the output feature map in terms of the coordinates of masked tokens. To set a baseline with the transformer decoder, we follow MAE and some existing ones to design the pipeline. The transformer decoder accepts as input visible tokens and masked tokens with shared learnable embeddings. Several flat transformer blocks are then applied to recover the features of masked tokens. We compare GD-MAE with other models on the Waymo dataset with a single-frame LiDAR input. GD-MAE achieves new state-of-the-art results among all single-stage detectors on the Waymo validation set. Equipped with a refinement network, GD-MAE surpasses all previously published methods. We also evaluate the performance of GD-MAE on the once validation split. It achieves significantly better detection results than previous strong detectors. We conduct a series of ablation experiments to study the effectiveness of the proposed decoder. Table 1 shows that GD-MAE can significantly improve detection accuracy with only 5% of annotated data available. Table 2 illustrates that GD-MAE can consistently improve the accuracy of different multi-scale encoders. And we found that GD-MAE brings the highest gain for the proposed transformer encoder, which suggests that our simple decoder is particularly suitable for the transformer-based encoder. In Table 3, we can observe that pre-training with the block-wise masking strategy brings less improvement than other methods, probably because the task is too difficult to learn effective features from sparse LiDAR point clouds. And the overly simple task is also suboptimal for efficient feature learning, while an appropriate difficulty level yields the best result. In Table 4, we discover that a ratio of 75% works best for creating a task that is adequately difficult for self-supervised pre-training. Table 5 shows that using more epochs can further improve performance, which demonstrates the learning capability of our model. To prevent overfitting on the same dataset, we pre-train the model on the once dataset and then fine-tune it on the Waymo dataset. As shown in Table 6, GD-MAE consistently boosts the accuracy of all categories. We illustrate several examples of the reconstructed point clouds on the Waymo validation set. The model catches the distinctive LiDAR scans along the ground plane and demonstrates a knowledge of the basic geometry. We also demonstrate qualitative results of the downstream detection task, which could predict distant and highly occluded cars. This is the end of our presentation. Thanks for your watching.